had a photograph in the previous lecture I gave on corrosion of steel. So this used to hold as a single piece years ago, and when I found it, it was layered. Obviously, I could see that, but it wasn't clear to me that it was just rust. So I had to go back and ask Professor Eager essentially for what he thought of it, and I did some testing as well. The bottom line that we discussed last time is rust will expand, and that's a good example because it came out of a beam that was approximately 3/8 to half an inch thick. So had this been, not expanding, would be essentially corroded through. It's something that can happen, but it's definitely not desirable when you're looking at structural flanges. It happens with steel piles. I had a project in Hartford, Connecticut, where they went on and were driving sheet piles. These are essentially corrugated steel. They're doing it right now in into the Charles River, close to I think it's River Street. They have this little hammer that is driving slowly sheets that are about 4 feet wide by 20 feet long, and when they're done with one, they connect another one to it, and they keep essentially building up a wall to retain water, to provide some soil integrity for any kind of settlement. But years down the road, if you put this much of steel, years down the road, you can have holes through those piles. So for all the geotechnical engineers, it's a big uncertainty as to how good the pile is, depending on exactly how the environment conditions are. We talked about 2 mils per year of degradation, but that varies from almost zero to higher values, depending on the local environment. As you go below the water table, it tends to be more constant because it's a homogeneous environment. But right between the water table and the dry soil is an area where there's a lot of fluctuation. And I've seen that as well on underground storage tanks for gasoline or oil, where the top looks pristine, but the bottom has a lot of damage. So today we're moving on a little bit. From steel, I want to emphasize some of the reasons for going to lighter materials like aluminum. And we're going to go through one concept that I wanted you to take out from the class overall is this material properties ratio charts, or HB plots. There are multiple names for it. Essentially, it's plotting one material property against another so you can compare materials. And yeah, we're going to talk then more specifically about aluminum alloys. So this is a very large overview, and I'm trying to make it as big as it is, but the scale on the horizontal is density on a log scale. So we can say that engineering material will vary in density by a factor of about 1,000. It's very significant. So depending on what you're looking at for an application, you may be looking for foam on the core, for example, of a composite, or you may be looking at a very high strength alloy for a thinner member that are heavily loaded. The other axis that I put on is the strength. And that may not come to you as absolute, but there is a certain correlation between density and strength. So something that is heavier tends to be stronger. But we have room for improvement. And the reason for these dotted curves here, well, see, we have metals that are high up there, and we have ceramic. They are lower density, but they can have about as much strength, but they're generally not. So that's why we don't use just ceramic. Otherwise, we'd be very interested in terms of strength into ceramics. Composites are really high. You can see that as well in terms of strength for a certain density. They're above that green lines. The green line I put on is a copy of this one here for bending applications. And we can go over what that means in detail. Essentially, you can decide on how much you care about the ratio of strength over density, depending on whether you have a tensile application or whether you have a bending application. Because in a bending application, you care about the sectional moment, the thickness. If you have a material that's light like wood, you can have a whole beam of wood that would be stiffer for the same weight because it's much bigger. In tension, those considerations don't come into play. So if we take this curve here, where the strength aspect is only half of the importance of density, that's where we end up selecting these foams and wood components. We really start becoming more sensitive to, we don't mind too much how heavy it is, essentially. In tension, that's this curve here where you have the stress over the density. You're looking, if you keep moving up here to maximize the strength over the density with a slope of 1, you'll end up with these ceramics and composites, and the reason, again, we don't use them too much is toughness. So there's always some level of compromise to be done, but sometimes this is a starting point, and if you don't know exactly what you're looking for, we have a project right now where we're looking for a material that is low strength and high conductivity. Well, we have copper, but what else is out there? So that's the kind of charts that we can look at to determine what the options are. If it's conductive, almost needs to be a metal, but then, what kind of metal are we looking at? So that's what we're looking into. This is another plot here where we're looking at fracture toughness. I mentioned fracture toughness for critical components. A lot of times you want them to be able to withstand a certain amount of defects. So if you are high on this chart here, and we again have the composites. If we take a 1-on-1 slope density against toughness, one of the highest components here is all these composites. Because of the reinforcement, they combine a great combination of low density from both the matrix, but also if it's glass fibers or carbon fibers, it's relatively low density as well. And these fibers can essentially bridge cracks. So if you have a crack trying to go through the material, say I have some fibers here, I have one there, and I'm trying to crack between them. And this is a topic we introduced before, that it's always nice to have the strength of the material active in shear. So in this case, if the fiber is strong enough, it's making, this is the crack tip here, it's making a bridge between the upper portion of the crack and the lower portion of the crack, to the point where the force transfer is going to be over a surface area here. This surface area is in form of adhesion, and Professor Igor talked about adhesion in his portion of the class. It's not the strongest bond, but you have it over a large distance, and you can think of it this way: is you can start, maybe you have a little debonding at the beginning, but it doesn't mean it extends all the way. So depending how long these fibers are, you will be able to gain from this bridging effect or not. There are some composites that are short fiber glass, in nylon, for example, and it will depend on the size of the crack whether you can bridge here or whether the crack is actually going to debonded completely, and I've observed those myself on a fracture surface. Sometime on this composite with short fibers, you see the individual fibers sticking out. So the crack actually made its way through all around and ignored all your effort to slow it down. But if you have continuous fibers, you're really getting away from this trouble. Obviously, the other limit is when you start having too much stress on the individual fiber, you may break some of them. That's not impossible as well. But they are essentially a tie between the two surfaces that would not otherwise exist in this relatively low strength resin. Typically, the resins are not able to take large amount of stresses. They are able to strain, and that's where when you have that crack opening here and you distribute it up and down, that you can stop a crack effectively. So on this fracture toughness chart versus density, that's why we see an advantage. We can already, I know I'm going into different failure modes here, but we can start, I think it's good for you to start thinking what happens if now I have a cyclic deformation. If I have a cyclic deformation, I'm increasing the risk of disconnecting that bond. Say on the first time, maybe I disconnect from here to here, I have some viscoelastic deformation that's holding up there. Next time I come around, I continue, and then I progress into my debonding mode in fatigue of this type of structure. So it's not because if I make a pre-crack and I try to break it, it's much stronger. That would necessarily be the case when I do the cyclic loading test. So especially in the case of a composite, you don't want to base your design, if it's going to be cyclically loaded, just on the fracture toughness. You need to look at the fatigue crack curve as well. This is more specific to the, we have more specifically on some stainless steel alloy, aluminum alloy, steels. So we're looking here at a relationship between strength and fracture toughness. That's one that I discussed briefly when I introduced steels, that you can tailor the steel to maximize one or the other. I would say this is a good example of it, that if you look at the arrow for steel, it's fairly wide. It goes all the way from a ratio of 10 to the minus 1 to 10 to the 2. So when we're talking about, are we going to use this alloy, this alloy, this alloy, or this alloy, this category of alloy, obviously we need to pick representative candidates for each category. So if we're looking for the maximum fracture toughness and a good strength, we are on the strip type steel, maraging steel, very high performance steel. That's where we will try to compare with a good titanium alloy, for example, if that's what we're looking for, a combination of strength and fracture toughness. If what we're looking for is mostly toughness, you can see there's a drop here in most of these curves where the woods and the plastics in general would have sort of a better strength than a toughness, comparatively speaking. And that is not necessarily surprising, and it's consistent with a lot of the use. We tend to use plastics a lot when they don't absolutely need to be resistant. If you have a few failures that are not catastrophic with a plastic, it may be the material for the application, because you can make it at very low cost. It's easy to finish, but if you say, oh, I have a scratch on it, is it going to break? It's a lot more likely to happen with a plastic than with most metals. So it's very sensitive to notches, large imperfections, and it shows here in terms of the lower fracture toughness. When we have a plastic, and I'll make that point more clear when we talk specifically about plastic. If you mold the plastic into a shape, so say I have a mold and I'm trying to make a shape that will look like this. So this is my injection point. And even before that, I have material that's flowing inside the screw system to heat it up and blend it. When I inject it, it's very viscous. And the viscosity tends to orient the polymer in the direction where I push the fluid. And I have some effect near the end because it can't move like that. So this would be an example where you have texture. So if you try to grow a crack like this in a notch like this to go this way, you'll have a harder resistance of the surface, especially the skin. The skin of an injection molded part is better than if you take a piece of plastic and you machine it. Because it has its natural orientation that's favorable for loading it perpendicular to the injection molding direction. I don't know that this has already been taken into account here. It may be a supplemental effect as far as reducing the strength. But the idea is when you have a plastics, it's harder to use the fracture mechanic background I introduced to you a little bit. It's common to think of it as it will be able to take a fair amount of load, but not necessarily a repeated load, not necessarily a sustained load. If you have a constant load on an unreinforced plastic, you need to design it to allow it to expand. And that's the example with the polyethylene piping that Professor Eger mentioned, that they didn't want to deal with corrosion anymore, so they decided to use high-density polyethylene. But the cost aspect of that was to make a very thick wall, so the stresses are sufficiently low that the creep, the deformation that happens over time, is still negligible within a 25-year exposure cycle. So it just becomes a different requirement. It's strength. Strength relates to the viscoelastic as well. So if you think of a plastic as relatively high strength than another, most likely it will also have less viscoelasticity, less deformation over time. And we definitely can go through that. This is just another plot to show the difference between alloys. I was going through it recently looking for high thermal conductivity and a low thermal expansion coefficient. So for me, I would like to be in this region of the spectrum, but diamond is too brittle for me. Silicon would look really unusual for the application, but this gives me some things to work with, some ideas that I could push further if I wanted to, because those are the two properties that are important for my application. There are hundreds of these charts, and you can, I believe with the link from the library, you may be able to generate your own with ASM. Not necessarily, there are softwares commercially available to do it, but I believe in ASM, if you can't do it, you have a large database of them that you can look at. So if you're interested, that's definitely something to do. I wanted to point out to you those different indices because they come handy in a number of applications. So for tension, that's the tie, the first one. We have the force against the density is what the yield strength or the failure strength against the density. That's what we're trying to maximize. It's not uncommon to have this case if you have a rope it's a straight tension. If you have some simple members in a system that you know are going to be simply loaded, torsion, you can see that it all depends on where you look at the load, where the load is applied. For bending, it's the same story. If you are more specific about, in this example, what is specified, that you want a specific height, it's almost becoming back to a tension situation. So that would be the case if I design the web portion of a truss or a rib or any kind of structural component, where I need to ensure stability against buckling of the thin portion in the center. When I mentioned about those titanium ribs, for example, you need a certain amount of material in the middle, so maybe you need to have a certain height, in which case you don't have a benefit. But when you can change the height, that's what you can. And that's where, for example, if you decide to use a different alloy, that like between aluminum and steel, if here the strength is less important than the density, you're more likely to go for which one? Strength is more important than the density. So you're more likely to go with aluminum, I think. If the density, well, let's multiply this. The density becomes more important. So aluminum will win here, yeah. If the strength is more important, that's a situation where you may still want to use steel, even though it's a higher density. So you have to think a little bit if you're doing a design in tension or compression. And that's what I was faced with when I looked at those titanium ribs, where at least 2/3 of the design was more for compression and buckling than it was for strength. So going from titanium to steel was really not a great option. The only advantage that the steel could provide, and that was even possibly, it was for the tension part. Everything else was better off of a material of lower density that you make thicker, that's more resistant to buckling. These are similar indices, but for fracture toughness. It's for against the pressure. We'll look at these beams here again. For displacement control, essentially you're trying to. Most of these are linear. Because it's mostly for tension. So think of tension as being more or less a linear relationship between the material property you're looking at and the density. It's mostly when we get into a compression or a bending situation that we need to take into account, minimum thicknesses for buckling and bending section moments that increase with increased thickness. And yes. The flaw tolerance here is just K1C. That's how it means that you get a better combination of crack length and stress level resistance. One thing that is good to think about is the difference between, if I'm designing a tube, there's a difference between designing it for the overall load or local buckling. And so for local buckling, that's something that can happen if you're trying to make a bicycle of steel bicycle, you really want to make the tubes not too big, not as big as the aluminum one, because otherwise you'll dent it locally. I mean, it's able to take the overall load and be very stiff, but you have to take it down so you have enough thickness that you won't punctuate into it or create an instability. So it's different than those simple equations. You have to go through another equation for local buckling, which is pretty much asking you how much load do you want to be able to take. So if I have a design for a bicycle that I'm trying to compare aluminum and steel, it will be a very different shape. And I think you already know that from the beginning, but the way you optimize each of the shape is based on, one case, more of a local buckling effect, but also the joints. I mean, aluminum has lower strength joints, but if you weld bigger tubes together, your moment of inertia between them is more favorable, and you don't have any brittle behavior that's expected if it's welded correctly. So there are advantages to both materials. It's just, when we're talking about a significant change, we're changing density by, say, 2.5, a lot of other things should be done the same way to be able to optimize both designs. Speaking of aluminum alloys, last class I talked, well, the two last class I talked about steel. I first talked about the mechanical, and then I talked about more corrosion type review. Today we'll do aluminum both for mechanical and corrosion. It's not quite as complicated, I would say. I'm presenting to you here the conventional series of aluminum from the Aluminum Association. The numbers are not that clear, but it goes from 1,000 to 8,000. It's organized where the 1,000 series is the most pure level of aluminum. It's the one that's electrically more conductive. It's also the most resistant to corrosion. One of the reasons it's resistant to corrosion is there are no precipitates, there are no inclusions in the material that will act as preferential sites to start a corrosion. As you know, aluminum gets its good general corrosion resistance from the natural passive layer that builds on it. And we talked in the last lecture, I showed you the poor bear diagram, where this only works nicely between a pH of 4 and 8 or 9. If you're outside that range, you're at risk for accelerated corrosion. Well, if you look at the other alloys here, you can also have significant corrosion, pitting, deterioration of the finish, and you can have stress corrosion, cracking, even if your pH is seawater or a normal, nearly neutral pH. If you have chlorides and other impurities, that's what drives the deterioration of the aluminum. We do alloy the aluminum, therefore, for strength. It's not for corrosion resistance, it's not for conductivity, it's for strength and toughness. And the different series here, this 2000 series is fairly well known in aerospace, has copper in it. The idea for that is to put the copper in solution with the aluminum. So both aluminum and copper are the same crystal structure. So at high temperature, you can mix them together. And when you cool, if you cool fast enough, you're going to prevent the formation of other phases in the material. You keep it at what we call a solid solution. So that's quenching. And then you go through one more step that we call aging, where you heat it back up just a little bit. It's not very high temperature, and you help the formation of very fine precipitates or a dispersion of precipitate that's going to increase your strength. It's like making very strong barriers against the dislocation in the material. It's a different process than everything we talked about for steel. For steel, we were talking about all the carbon and everything just sort of staying in solution, and then we have this Martensitic transformation where here, when you cool it down, nothing happens. It doesn't become brittle. It's the same whole thing you had at high temperature. It's useful in aerospace because you can relatively easily do that process of heating them up, quenching it. You get some distortion in that process, and then you form it. So you go and say, oh, I want, you know, the front, the nose of the aircraft, whatever it is. I want this radius, this radius. It goes on the table, and you stretch it in 2 dimensions. Stretch forming is common in aerospace. When you're done with this, now you heat it up, and you increase your strength. So it's an effective way of increasing the strength. Another way that you can do this is a nice joining application. When they quench a certain type of 2000 series aluminum alloys, they keep them in the freezer to prevent aging, because they make that chemistry so tight that by keeping it at ambient temperature, it's going to age. So when they make the assembly, they forge the rivet within 12 hours or whatever it is. It will gain the strength that they wanted to achieve by aging at ambient temperature. They don't have to cook the whole assembly. It's a pre-operation of quenching, no properties change, very ductile, very soft, form it, and then let it age. So it's something to keep in mind. Not all the alloys. So in this table, for your benefit, what we talked about is the heat treat type of alloy, and it's all more or less the same principle. You form small precipitates, different kinds, and depending what you form, you get a different compromise between yield and fracture toughness. And then you have a few series of alloy, the 1000 series, 3000 series, some of 4000, 5000 that are cold work. So those alloys, you don't get a whole lot of a benefit by trying to quench them and aging them, but all the others you do. It's fair to say that 3000 and 5000 series are considered better for corrosion resistance, mostly because they don't have these precipitates. So if you go and you're looking for an application where you don't want to deal with stress corrosion, it's the 1000 series, then you have 3000 and 5000, and that's why 3000 and 5000 are used for bolts, for making the holes and all the things like that. They also weldable. Well, all the aluminum alloys are weldable, I should say. This is just really to give you an idea for the alloys that are deformable, how much strain you can actually put in them and still increase the yield strain. Any of them, we're up here at 100%, and it's still going up. So it takes of the order of 200% before you actually reach a fully hard condition of these alloys. So when we're looking at a stress strain curve, that's an exemplification. If I report 30% elongation at break, it's from tension. If I have a rolling application, I can deform that aluminum to a much greater extent. So it's to just give you an idea. So I was very serious about how much you can increase the hardness by these little heat treatments we talked about. So we talked about solutioning it, so heating it up in a region where both the copper and aluminum, they share the same crystals. They all agree with each other. You quench it, nothing happens. It doesn't harden, it doesn't go through martensite. you can do your forming if you want. That's what I put as stretching. And the aging gives you these little particles in the system that are copper rich or magnesium rich, depending which series you're looking at. The type of hardness evolution you get, a bunch of curves here for different aluminum alloys. So let's just go with the higher copper content. So our hardness goes from 55 Rockwell B all the way to, say, 95, but it goes to a peak at 110. Well, that's kind of the story of aluminum alloys is you can use them in any of those states. And we use the designation T for the treatment that's applied to it. If you have a T6 treatment, it means you're at the peak. Anything before 6 is typically be below, and T7, which is not uncommon, especially for 7000 series, is after. Now, if you go to a T7 here, one of your advantages, you can have bigger precipitates that are not going to interact as much in, say, stress corrosion cracking and other mechanisms. So there are reasons in terms of environmental resistance to go to an overage as opposed to an underage. The underage in general will give you more hardening. And therefore, if you're looking mostly for mechanical properties, you prefer to be slightly underage. And I have an example of that because I tested that in my thesis. This graph may actually be in my thesis. I don't know. This is essentially comparing the same plot of hardness as opposed to the aging time. I tested a material that was here against a material that was there. So before the peak and after the peak. And what we're looking at here is the profile of a scratch. So I came with a conical indenter, plowed into the surface, and made a scratch under a constant load for enough time to get a constant profile. So I imaged that profile. So we're looking at a cross section that's normalized, and you can see maybe a factor of about 2 in how much material is getting pushed out of the scratch to the side when you have that overage condition. And that's an exemplification that you have less hardening. If you have a material with a lot of hardening in the normal indentation test or a scratch test, it will essentially consolidate and it will not extrude out as much material as a material with a low hardening. If you do butter, it will plow it, if you try to displace a certain volume, it will plow it on both sides for you. If you do a material that's very hardening, it will essentially boost the whole surface on you as opposed to just moving it in front of you to the sides. So it's just to say that you always deal with a compromise. In this case, we talked about strain hardening and scratch resistance as opposed to all corrosion resistance. General corrosion resistance for aircraft applications is normally not too terrible because we have the anodizing treatment and we have the paint applied to it. Stress corrosion cracking, however, becomes a long-term issue when you want to minimize your repair cost or increase the load on the component, because most of these alloys will end up stress corroding, and we'll go through that a little later. This is something that just like for you to keep in mind about joining anything, in this case aluminum. You'll have distortion and you'll have residual stresses. If you prevent a distortion, typically it becomes a built-in residual stressor. And that's what I'm showing here when going and making a cut here. looking at the stresses in the weld. You have tension in the direction of the weld here, and far from it you get the equivalent compression. It needs to equilibrate over time. And the reason you have the tension is the metal is really hot. And when it cooled down, it tried to shrink, but all the material around it just prevented that compression. So that's a good exemplification of it. It always happens. It will only be a problem if material is very susceptible to stress corrosion cracking, for example. Well, it can be a problem for other reasons as well. If you make a design that has a number of connections and there's some load applied below the yield stress, if you look at the structure as originally designed, but because of the residual stresses, you'll have some areas that will actually move, that will actually create a permanent deflection because they're already pre-stressed, and that's not something that we generally take into account in the analysis. It's one reason why if I weld something out of steel, sometimes I can bang it to straighten it because it already has enough stresses in the alloy that it's close to yielding, and it's easier to deform that joint than if it was completely annealed and stress relief. So there are options to avoid that. You can stress relief. Specifically for aluminum alloys, you get a reduction in yield strength if you're going to weld an alloy that was aged, which is often the case. So a 2000 series, a 6000 series, or a 7000 series aluminum. And people sometimes think about strain in the heat affected zone in the weld, so they want to use a different electrode, try to make things better. But my experience has been that in the heat affected zone is what you really worry about because you're not making any changes there. You know exactly what the chemistry is, and when it heats high enough to bring back these two components we talked about, aluminum and copper together, and then cool it down again, there's no aging anymore. It's gone. So that's the pitfall. You can the very specific example is aluminum 6061 T6, which is used for welded structure. You start with a yield around 40 KSI and then you're down to 15, just close to the weld. And there are ways to design with that if you are willing to have lower stresses in your joint. And that's, we talked about making a lap joint that's working in shear. But essentially, if you try to take two tubes, I've seen that on aluminum ladders. That was not pretty. Two tubes welded together to continue, these sides of a ladder. Well, you don't get the same benefit out of that one area you welded and everything else in the structure. And what's the justification for that? Everything else is 2 or 3 times too strong. Normally not. So you just can't do that. You can't substitute a heat-treated aluminum for an aluminum weld at all. It doesn't matter if it's a casting, it doesn't matter how good the weld is. It will, if it's heat-treated, you will lose the strength, the yield strength. I've put this chart, and we already talked about corrosion quite a bit. This is going through some of the details and what changes the resistance, which alloys have relatively more resistance to general corrosion, pitting, and stress corrosion, cracking. It's very unfortunate because some of these alloys here, I'm looking at 70, 75, are very common in aerospace industry. So I would say it's an exemplification that in that industry, yes, we want to know about corrosion resistance, but most of the times it's density and strength that end up being the deciding factors. And then you have to control the cracking or the pitting if you have any. the few alloys, so we have an alloy, the 5000 series that's got an A for boat, general stress corrosion cracking. So yeah, you make a boat out of that because you don't mind if the boat is just a little heavier. If you can weld it and resist the corrosion. And we have the 1000 series aluminum that's also more resistance. So I hope you will remember these material property charts. When you have a project, it's a question of getting familiar with it. All the textbooks that have them typically give you a few examples of how they came up with it for different loading conditions. For aluminum alloys, I try to give you a decent overview about difference between rolling it or heat treatment. So rolling, we had 1000, 3000, 5000, and the heat treatment grades were the other one. Without the heat treatment, you have benefits of corrosion. The heat treatment gives you better strength. So that's pretty much what you need to know about that. The joining of aluminum creates softening and a reduction in properties. So if for steel, for example, everything considered for static strength, now you're moving to fatigue. Say you cut down the stress level by about a factor of 2. It's not uncommon based on the aluminum design manual when you have a weld to cut down by a factor of 3. And that's to account for variability. It's slightly harder to weld aluminum. You can have more impurities. It's not as easy to use the slag that we talked about. You have to use inert gas generally. So in terms of corrosion resistance, it's typically inverse with the high strength. So you have to know what you're looking for, and that's why in the industry, if you want a piece of aluminum that's corrosion resistant, you go see a sailboat manufacturer. He's got his whole yard full of 3000 and 5000 series. And if you're looking at a very high strength structure where you can afford to do some anodizing to seal the surface, then you'd be looking at these heat-treatable grades. I've been going continuously the whole lecture, so any questions, anything you guys want to talk about? You looked awake, but...
You want to talk a little bit about your presentations or homework sets or term papers. You start thinking about what you're going to do.